Welcome back, students. We left off last lecture wanting to discuss formulating the molecular partition function for each individual degree of freedom. If we do this, we can describe the canonical partition function, which we can in turn use to figure out the bulk properties of the system, such as internal energy, enthalpy, entropy, heat capacity, and so forth. And we can do all of this based on nothing more than quantum mechanics. So the learning goal for today is going to be to simply calculate the translational, rotational, vibrational, and electronic partition function using the appropriate quantum mechanical energy level spacings for those degrees of freedom. We'll derive these in this lecture, but the result is just going to be a mathematical equations that we can use to calculate these based on a given molecule, volume, temperature, and so on. We'll start off like we did last semester with the translational degrees of freedom. So what we'll need to do first is recall the energy levels for the particle in a box. The energy levels for the particle in the box were a function of the quantum number n, and they were simply h squared n squared over 8ma squared, where n is our quantum number, h is Planck's constant, m is the mass of the particle, and a is the width of our one-dimensional box that we can find the particle to. So if we recall from last lecture, our partition function is always the sum from n to infinity of our e raised to the negative beta times the energy level. So e to the minus beta epsilon n. And we can plug in our value here for what epsilon n is to find that our partition function for one-dimensional translation is equal to the sum over n of e to the minus negative beta, when remember beta is simply 1 over kt. So beta times h squared n squared over 8ma squared. Now we have a problem because this is an infinite sum that we can't really evaluate. So how do we solve it? The trick is recalling that these energy levels for translation are very closely spaced. And we have a very large number of them being occupied. Since this is the case, the sum isn't over 2 things or 3 things, but rather, 20 million things. And it's actually pretty appropriate to change this sum into an integral. So rather than being a sum from n into infinity, we can approximate this as the integral from 0 to infinity of e to the minus beta h squared n squared over 8ma squared with respect to n. Now, this actually has a solution. So this is something that we could look up in the back of our book. We've done this integral last semester. This integral ends up simply being 1/2 times the square root of 8 pi ma squared over beta h squared. And what we'll do is rewrite this as the square root of 2 pi m over beta h squared. And we'll pull out the a there, so we'll have a. And this is because a is the box length. So pi is a constant, the mass of the thing is a constant. We have kt, we have Planck's constant. And we can group all of these things together into what's called the thermal wavelength. So we'll say that the thermal wavelength, which we'll denote as capital lambda, so capital lambda is then equal to 1 over this term here. So h squared over 2 pi m, and we can simply define the one-dimensional translational partition function as a, the box length, over lambda. And we can also write this out if we want, and sometimes we'll do this if we don't have lambda and we have the numbers. We can more easily evaluate this as the square root of 2 pi m kt, and then we have a over h. So we can actually evaluate this relatively easily. At this point, you'll probably object and say, most particles aren't trapped in one-dimensional boxes like we assume for the particle in the box. And this is, of course, true. Most particles are free in 3 dimensions. In some real applications, we can have 2-dimensional motion, for example, particles absorbed onto surfaces and so forth. but the one-dimensional model is kind of silly here. We can take the three-dimensional partition function, and it's simply going to be the product of all of the one-dimensional partition functions. So we can have translation in the x direction, translation in the y direction, translation in the z direction. And these are all independent. And so we already defined what one of these is. So we just did translation in the x direction. We can say that that is the x length of our volume over the thermal wavelength. And then translation in the y direction would simply be whatever the y length is. And translation in the z direction would simply be whatever the z length is. Now, what do we have? Well, we have three dimensions that are all, one-dimensional distances multiplied to each other. So what this is simply the volume over the thermal wavelength cubed in this case. And we can also write this out if we want to solve it as 2 pi mkt. And now instead of being the square root, it's raised to 3/2 because we cube it. And we multiply this by the volume now over h cubed. So this expression here will allow us to solve for the partition function for molecular translation. What should we expect this translational partition function to be? We can note that the denominator has Planck's constant cubed in it. We should therefore expect this to be a very large number. And if you're trying to do this in a normal graphing calculator, we've already seen kind of the opposite problem with weights. But Planck's constant cubed is a number that is smaller than 10 to the minus 100. So if you plug in h cubed into your calculator, it's going to give you an error. You can resolve this by simply dividing by h squared and then dividing by h. It has no problem doing that because the number itself isn't that large or small, but the h cubed itself is. So the numerator is actually quite small, which will combat our very large denominator. The Boltzmann's constant is small, the mass of the particle in kilograms is small, and so these two things will mitigate the overall very largeness that we would observe. Now, we can rewrite this expression if we want to rearrange for the mass in kilograms to kind of get an idea of what this would be. So if we assume room temperature, we can say that our translational partition function is going to be equal to 2 pi m. Here, this m is the molar mass of the substance in grams per mole rather than the mass of the single atom in grams. This is easier for us to calculate most times, times kT. Then we divide by 1,000 times Avogadro's number. And this is what has to be raised to the 3/2 to multiply by v over h cubed. So if we do all of this, what we end up with is that we get, our answer is 9.67 times 10 to the 29 times the molar mass in grams per mole raised to the 3/2 times the volume. So the molar mass of something in grams per mole is going to be on the order of 10, 20, maybe 100 grams per mole for something that's heavy. The volume needs to be in SI units, which is cubic meters. And so the volume is going to be relatively small. 10 to the minus 3 would be 1 liter. If it's a big volume, a room size, maybe it's on the order of 1, 2, 3 cubic meters. And so with this, we can see that the molecular partition function is actually quite large. And it's going to be very near, say, 10 to the minus 29. So if we plug in numbers for argon in a 1 liter volume, the mass of argon is 40 grams per mole. So we have 40 to the 3/2. And the volume for 1 liter would be 0.001 cubic meters. We plug that in and find that QT for argon is 2.45 times 10 to the 29th. In other words, a very large number. This largeness of this number is another way that we can show that this degree of freedom is very continuous. So the larger the partition function, the more likely that degree of freedom is to be continuous. We'll see for rotational and vibrational and electronic degrees of freedom that were much more quantized last semester in quantum mechanics, that they have much smaller partition functions than the translational degrees of freedom. Now we turn to rotational degrees of freedom, and we can recall the energy level spacings for rotation from last semester as well. So the energy level spacings for rotation were equal to HCB times JJ plus 1. And this is using spectroscopic units. So this B is a rotational constant in inverse centimeters, and B is based off of the molecule that's rotating as follows. It's equal to Planck's constant divided by 8 pi squared times the speed of light in inverse centimeters times the moment of inertia I, which is equal to 8 over 8 pi squared times the speed of light times the reduced mass of the bond times the bond length squared. And the energy level spacings here are not uniform. They increase as j plus 1, where j can be any integer from 0 to infinity. Recall that unlike translation, rotational degrees of freedom are degenerate. So for every rotational energy level, which we could either use L if we're talking about orbitals or J for bond rotation, the quantum number m sub L can go from negative L all the way up to positive L, which means that the energy levels are 2L plus 1 or 2J plus 1 if we're going to use the quantum number J, degenerate. The partition function then, so the partition function that we wrote before was always equal to the sum from n to infinity of e to the minus beta epsilon n. We left out the degeneracy term because it wasn't applicable for translation. Here we'll need it. So it's gn, the degeneracy of level n, times e raised to the negative beta times the energy of level n. We can plug this in as follows. So we can say that the partition function for rotation is equal to the sum of j equals 0 to infinity, and then we'll have what degeneracy 2j plus 1 times e raised to the minus beta HCB times JJ plus 1. To solve this, we'll do the same thing that we did above for translation. And we're going to rely on the fact that many rotational degrees of freedom are accessed for most molecules, which means we can again approximate this sum as an integral. For molecules where this assumption is not valid, such as diatomic hydrogen, which is very quantized in terms of rotation, the integral is not appropriate and the actual sum must be evaluated for every level that's significantly accessed. So we can say then that the partition function is approximately the integral from 0 to infinity of 2j plus 1 e to the minus beta HCB times j plus 1 with respect to j. We can use a u substitution here. And to do so, we'll recognize that this out here is going to be the j dependence of the derivative of this term in here. So what we can do is set u equal to minus beta HCB j plus 1, and that makes du with respect to j, it is simply going to be 2j plus 1 times negative beta HCB dj. And here we have this 2j plus 1. So plugging this in above, we end up getting the integral of negative 1 over beta HCB e to the u du. And we're evaluating this then, it's the same from 0 to infinity. We can go ahead and evaluate this, and we end up getting the following. We end up with 1 over beta HCB, and then with this, we can plug in what beta is. Beta is KT, and we end up with KT over HCB for our rotational partition function. We have to make one more correction for some molecules due to indistinguishability. If our molecule is symmetric, for example, this molecule here, when it rotates, if we do a 180-degree rotation in this direction, it's going to be back in the same form that it started as. And so for this, what we have to do is introduce another parameter that takes into account, again, overcounting due to things that we can't actually distinguish. We can't tell, if which of these atoms is which in any given rotation. So to account for this, we divide by a symmetry factor that reflects the number of identical states. So for this molecule here, it would be 2. So that would be the sigma here, and this sigma would be 2. Another correction must be introduced for polyatomic molecules. So these molecules that have multiple rotational parameters that are different, as can be seen down here, they have different moments of inertia and they have different rotational parameters B. So there would be a B, A, B, and C for the different dimensions that this thing can rotate in. And so we would have to multiply it together in this way for 3-dimensional molecules. So our partition function for rotation isn't necessarily as simple as 1 over beta HCB, but it's more or less the same thing here. So if we have 3-dimensional rotation, we need to have this sigma parameter that talks about the identicalness, the symmetry there. We have a square root of pi, and then we have 1 over beta HCB to the 3/2. Again, you can see the similarities for translation when we talked about 3 dimensions there as opposed to 2. And then we have BA, BB, and BC here, which could be the same or they could be different based on the molecule. It is often helpful to define a rotational temperature that we can directly compare to the temperature. And this is simply going to be all of the parameters in our partition function that aren't temperature. The rotational temperature gets a capital theta with a subscript r to talk about rotation. And this is simply HCB over the Boltzmann's constant. Now, doing this allows us to define the partition function as simply T over the rotational temperature. And then we need that sigma there if we have a symmetric molecule. What we can do is say that our rotational partition function is equal to the temperature T divided by the sigma that talks about the identicalness, different rotations, most states being identical. And then we have our rotational temperature theta. And this is the definition of a partition function, and it can be a little bit easier to compare some things. One thing we want to do is know when it's appropriate to assume that the rotational energy levels are accessed continuously. And in general, we do this if the ratio of the temperature to the thermal temperature theta is greater than or equal to 10. If it's less than or equal to 10, if it's a small number, the partition function will be small and only the lowest energy states will be accessed. And this can be vary based on the molecule. So for NO, something that's going to be relatively continuously accessed, we can see that the rotational temperature is about 2.5 Kelvin. So at 298 Kelvin, we're going to be at a T over theta of greater than 100 for this molecule. However, for hydrogen, we mentioned before that hydrogen is not very continuously accessed. Its rotational temperature is about 90 Kelvin. So the T over theta there is going to be something like 3, and it won't be appropriate to integrate over that since only a handful of rotational levels are actually accessed at room temperature. Now we will turn to vibration. We can recall from last semester that using the harmonic oscillator model, the energy level spacings for vibration are equal to hc nu times n plus 1/2. And the nu here is a vibrational constant, just like our B was a rotational constant, and it's equal to 1 over 2 pi times the speed of light in centimeters, and then times the square root of the force constant for the bond over the reduced mass of the molecules in that bond mu. We can plug this now into the equation to get the vibrational partition function. The vibrational energy levels are not degenerate, so we don't have to worry about that. And we can have that QV is equal to the sum n equals 0 to infinity of e to the minus beta hc nu and then n plus 1/2. Recall that the energy levels for vibration are typically spaced far apart relative to the temperature. This means that the integration approximation we have been using is generally not appropriate for the vibrational partition function because there are normally only the ground state being routinely accessed at room temperature. However, we can solve this infinite sum using a Taylor series identity. So the identity that we're going to use is that the sum from n equals 0 to infinity of e to the minus nax, where n is our integer, is simply equal to 1 over 1 minus e to the minus ax. So that means our sum up here is equal to the following. What we're going to do is pull out the 1/2 term. So this is equal to the sum from n equals 0 to infinity of e to the minus beta hc nu n, and then times e to the minus beta hc nu over 2. And so if we take this term out here, we can have our simple sum, and we can say this is equal to e to the minus beta hc nu over 2 divided by 1 minus e to the minus beta hc nu. And this is our solution for the vibrational partition function. This expression takes the 0-point energy into account in this numerator here. However, you'll recall that I mentioned earlier it is often advantageous to remove this 0-point energy. Before, I said I wasn't going to derive it then, but I'll derive it in the future, and now we are at the future. So here we're going to see that this is actually an appropriate thing we can do. So consider calculating the probability of measuring a vibrating bond being in a certain energy level. Well, the probability of that bond occupying a certain energy level is simply equal to e to the minus beta hc nu n plus 1/2 divided by q. So if we use the q that we have above, what we end up with is e to the minus beta hc nu n plus 1/2, and then we'll divide this by q, and q is e to the minus beta hc nu over 2 divided by 1 minus e to the minus beta hc nu. And you'll see that what we get is this term, this n plus 1/2, we can also substitute in this here for it, just like we've done before. So I'll go ahead and erase this term, and I'll put in this alternative formation of it. With this, we can see that we will cancel out both of these terms here, and what we'll end up with is e to the minus beta hc nu times n, and then times 1 minus e to the minus beta hc nu. Now, if I were to do this without using the 0-point energy, what I would have is simply e to the minus beta hc nu n, and then divided by q. Now, q would not have this 0-point energy. So q would be 1 over 1 minus e to the minus beta hc nu. And you can see what that gets us is the exact same thing. So when the 0-point energy is included, it's both in q and in individual energy levels. When I take it out both of the individual energy levels and q itself. So again, since what I'm comparing is really the relative difference between these different energy levels, if I set them at some 0 energy or I rescale them all to 0, I end up getting the same answer. And it actually is okay for us to do and makes the problems a little bit easier because we actually have a 0, which is a little bit more convenient. For polyatomic molecules with multiple vibrational degrees of freedom, the total vibrational partition function is simply the product of all of the individual partition functions. So we can write that QV total is equal to our capital pi that we've become familiar with now, from I equals 1 to 3n minus 6, or 5 if it's linear, of all the individual degrees of freedom there. Just like for rotation, we can also define a vibrational temperature that is Hc nu over the Boltzmann's constant. And we can do the same thing. We compare the ratio of temperature to the thermal, the vibrational temperature here. And if that is greater than or equal to 10, it's appropriate to think vibration is in the classical limit. Now, this is generally not going to be the case. So we can see here for iodine, which is something that has a very low lying vibrational state, that the vibrational temperature is 299 Kelvin. So the ratio of T to theta V would be about 1, which is not 10. So most bonds are not going to be continuously accessed in terms of vibration at room temperature. So it's never appropriate to use the integration here. Now, that's at room temperature. If we're not at room temperature, we can use the integration. And what that actually gets us is that the vibrational temperature becomes approximately simply T over theta V. Now, that is only true if we're in, again, this classical limit, this continuous limit. For most cases, we're not, and we have to actually evaluate this sum and get this term here. Lastly, we can calculate the partition function for electronic degrees of freedom, and we can use our model of the hydrogen atom. So for the hydrogen atom, the energy levels are the mass of the electron times the fundamental charge to the fourth over 8 epsilon naught h squared n squared. These are degenerate. They are 2n squared degenerate for the hydrogen atom. For other atoms, the degeneracy is more complicated, and we did some of this last semester. Just like last time, we'll remove the 0-point energy like we did for vibration, and we already saw how appropriate this was. And then we can calculate the electronic partition function. And the electronic partition function is, again, the sum from n equals 1 to infinity of all of the different levels. So we have 2 times e to the minus beta hc times 0. And then we have the energy for the first excited state, the second excited state, and so on. Now, what you'll see is that this is a small number. So since the energy levels for electronic degrees of freedom are so far apart, right? Even this first excited state here, 8 times e to the minus beta hc 82,303, that's essentially going to be 0. And so will every higher order energy. The only thing that will actually appear is the ground state, where we set the ground state to be having 0 energy, and then e to the minus beta hc0 is simply 1. And so what this means is that for most molecules, Q sub E is simply the degeneracy of the ground electronic state. And this is true for many molecules. It's not true for every molecule. So things like transition metals tend to have a lot of low-lying accessible electronic states, which is why they can appear colored in solutions and so forth. But for most cases, we can assume that QE is simply the degeneracy of the ground electronic state. Like for vibration, we can also calculate an electronic temperature. This is insanely large here. So we can see that the electronic temperature is 118,000 Kelvin. So it's basically never going to be appropriate to use a continuous spectrum for electronic degrees of freedom. At this point, we can put it all together to figure out what the total partition function is. Remember, the partition function is simply the product of all of these various partition functions that we've been calculating. So we've solved for all of these. We can go ahead and plug them in. For translation, our partition function was v over lambda cubed. For rotation, our partition function is 1 over sigma beta hcb. And for vibration, our partition function is 1 over 1 minus e to the minus beta hc nu. And for electronic, our partition function is simply the degeneracy of the ground electronic state. Here we have assumed we are working with a diatomic molecule. We could do it for a polyatomic molecule, but it would be much more complicated since we'd have many vibrational degrees of freedom to go along with it. What is the partition function? Well, as we've seen, the partition function for translation tends to be on the order of 10 to the 29. The partition function for rotation tends to be about 100 in that sort of range. And the partition function for vibration tends to be in between 1 and 2. And then the degeneracy of the ground state is often 0. So putting these things together, we can see that we typically get for a partition function something on the order of, say, 10 to the 31 to 10 to the 32 is the kind of value we expect for a partition function. One last thing to share before we leave is the equipartition theorem. We've used the equipartition theorem all the way back in our first lab in the semester. This theorem states that each degree of freedom in the classical Hamiltonian, that is quadratic with respect to momentum or position, will contribute kT over 2 to the average energy. Each translational and rotational degree of freedom has one such term that contributes quadratically with respect to momentum or position. And so each of those will contribute 1/2 kT to the energy. And vibration has two. It has the potential and the kinetic energy. So each vibrational degree of freedom will contribute kT to the energy. Now, as we saw in our first lab, this doesn't really work for molecules because the vibrational energy levels are not continuously accessed like is needed for this theorem to be true. So it works pretty well for rotation and translation, and we can kind of, in some cases, ignore vibration, but we can also incorporate them. We tried to do this in the first lab, and we'll do this in the next chapter, is actually be able to describe the heat capacity using quantum mechanics. So we could calculate why the heat capacity for something like carbon dioxide was exactly what it was. And these calculations are basically exact. You might remember doing some of this from the first lab. And we'll go ahead and do this in the next section. To conclude here, the main points for this section is the connection between quantum mechanics and thermodynamics. So we started with the canonical partition function and said that that was related to the bulk properties of the system. We then related the canonical partition function to the molecular partition function, and today we define the molecular partition function based on the partition functions of all of the quantum mechanical degrees of freedom. So putting all of these things together, the bulk properties of the system, such as internal energy, entropy, heat capacity, and so forth, are based on quantum mechanics, and we can actually use quantum mechanics to explain these bulk properties. And that's where we'll be going in the next chapter.